So next up, we have our lightning rounds. I'm Lindsay Fox. I'll be moderating the lightning round. So if you would all, I have a list of our speakers. You all have a number associated. If you would please line up in that order over here to my right. And while you all get organized, I am going to, here, let me zoom out here for a second. I think we have 23 speakers. So take note of your number. Once you've got your number, you should be able to fairly quickly organize yourselves. Okay, so while everyone is getting lined up, I'm going to talk to you just for a few minutes about a service that you probably heard about last year as well, if you attended last year's symposium. My name is Lindsay Fox. I am the research IT consultant that was hired to help implement a new service on campus. I say new, but it's new to me. We've been at service, I guess, now for over a year and a half. So I'm going to tell you a little bit about that and contextualize that a little bit for you all. So Research IT is a new service housed under the Vice Provost for Research, Padma Raghavan's office. We are separate from VUIT and all the other IT domains on campus. And for a little bit of context, here we are listed here next to student and administrative IT, educational IT, and desktop IT. We have a Research IT Faculty Advisory Committee that has been guiding us in our initiatives. This group is made up of 12 faculty and chaired by Associate Provost for Research Development Technologies, Doug Schmidt. Doug has stepped out for a moment, but you can talk to him more about this service as well after this. So our Faculty Advisory Committee has been charged, as well as the service, has been charged with several tasks. These tasks range from security and programming and network and storage resources as they relate to research. This committee also works to establish and triage priorities when demand exceeds available resources that we have on campus. We're also working to conduct a study on storage and computation needs on campus. I'll tell you a little bit more about that in just a second. We're also working to identify secure and compliant data processing needs and best practices for that. So we have 3 subgroups as part of our Research IT faculty committee. The first group is tasked with looking at storage, computing, and communication needs. So the largest thing to come out of this group this year is we tasked a group of technical experts, a subgroup of technical experts on campus to look at research data storage on campus. Many of you are aware of DOORS, the Distributed Online Research Storage System. The main task this group has been looking at this year is looking at the hardware infrastructure replacement for that system. We're very close to a solution, and more information will be coming out very soon about that change. Our second group has been looking at secure and compliant data processing. We look at a lot of different things, but the main and most important thing to come out of this group is an approval of a new data use agreement intake form. So Doug Schmidt, myself, this group, and SPA and VUIT have all been working together to come up with workflows for data use agreement intakes. Any new data use agreement coming to the university that requires a signature or an approval to bring data on campus will now be going through SPA. So a new intake form will be online and available through a portal shortly. But if you do have immediate needs for signatures on a data use agreement, please get in touch with us. You can email me at lindsay.fox@vanderbilt.edu. You can email Doug, anyone on the committee. And there's also some contact information at the end of this slideshow. I'm really excited to tell you all about some new training resources that we'll be having on campus starting in the fall. We have entered a partnership with the libraries to be members of the software Carpentries. Just a show of hands, have any of you heard of the software Carpentries? Great. So we will, as soon as hopefully everyone passes their training, but we will have as many as 7 instructors on campus, one including myself. Will French will be one as well. Jesse Spencer-Smith, he's in the back. Meredith Broadway. We have very many people on campus that are working towards getting certified as instructors. We'll be offering training boot camps starting in the fall. If you're interested in sending new research staff, graduate students to these training boot camps, we'll be focusing on basic software carpentry skills that are needed to do research here on campus. Another service to come out of Research IT is our Research Software Engineer for Hire and Consultation service. This is a new core service that we are providing to researchers on campus. If you have a need for a short-term programmer, think 6 months max for a project, you don't want to hire a full-time person, get in touch with us. We have resources that we're leveraging on campus to get this work done for you all. So that's just a little bit about the Software Engineer for Hire service. Again, I just talked to you a little bit about the new training that will be on campus starting in the fall. We also have a resources inventory portal. This is kind of a work in progress right now, but we do have a Research IT webpage housed through the Office of Research. And through there you can find this training, this resources portal, and get in touch with all of the resources that we're looking to catalog here on campus. So that's always a work in progress. So please come visit, come back frequently, and hopefully new resources will be up frequently. We're also working to create new research portals for the major domains on campus. The first one we've been working on is an Arts and Humanities portal. We also have a group that we've been working to coordinate support for Arts and Humanities with digital projects. That's a group that's made up of the libraries, Center for Teaching, and the Center for Digital Humanities. So if you're interested in more information on that, please let me know, or if you have comments or questions about what we're trying to elevate and promote through these research portals. Okay, that's basically all I have for you all. If you have feedback or questions or anything you'd like to get in touch with us about, please feel free to visit us through our REDCap survey, which is is.gd/researchit. You can also email myself or Doug directly. Okay, so is everyone ready for their lightning rounds? All right. We have 45 minutes until lunch. We have 23 speakers. I'm going to give you all, I'm afraid to give you more time because I don't want people going over. I have a timer for 2 minutes. If you use less, that's even better. But I'm going to hard stop you at 2 minutes. So if you're in the middle of a sentence, the buzzer's going off. Okay. I have your slide decks up here, so you'll just hit the next button when you're ready. Cliff, you're first.
Great, thanks, Lindsay, and thanks for plugging the software carpentries. So I'm Cliff Anderson. I'm Associate University Librarian for Research and Learning in the Vanderbilt University Library. And I'm here to just talk to you about the Buckhannon Fellowship that you're seeing up here. The Buckhannon Fellowship is an endowed fellowship at the library that is targeted towards undergraduates, where undergraduates and librarians work together to solve problems that are of practical interest to both and hopefully improve our library system. The reason I'm bringing it up here is that there are at least 3 that I think are relevant to this group, and I'd love for you to spread the word about them. They're on geographic information systems. So we have Dr. Stacy Curry-Johnson, who is our GIS specialist in the library, and she'll be running a group sort of introducing people to the basics of GIS and then hoping to solve some kind of problem together that'll, I guess, emerge out of their conversations at the beginning. There's also an interesting one on the evolution of the Peabody Esplanade. This is interesting because of interest to this group, I think, because we're going to be looking at historic photographs of the Peabody campus and then looking at the ways that the trees have moved around and to form actually the way that the campus looks now using GIS, and then putting that into a database, probably using linked data and RDF. So it'll be an opportunity to do something really practical and sort of fun related to the history of Vanderbilt. And I'll be doing something on a seminar on text mining at scale. So basically, we'll be looking at a framework called Spark Sonic, which is based on XQuery. It's a domain-specific programming language that I work with that you can query large XML databases. And so I'll be introducing that to people who are interested in large-scale analysis of maybe textual corpora. So with that said, if you complete this 10 seminars, it would get you, the undergraduate will earn $1,000. So that's the motivation. And the applications are open now. If you go to vanderbilt.lt/fellows, there's where you should point people to apply. So if you have any questions, please let me know. And again, thanks for your attention.
I'm trying to make this full view.
Oh, well, I don't really need a slide. My name's John Ayers. Oh, next. There we go. My name's John Ayers. I'm a geochemist in the Earth and Environmental Sciences Department. Most of my career, I worked with small data sets, and a few years ago with my students, started working on much larger spatially referenced data sets, and quickly learned that Excel was inadequate and that I had to relearn how to program. So I learned R about 2 years ago and was pleasantly surprised that it's much easier to program today than it was 35 years ago when I was an undergraduate. There's a lot of useful tools, and so we've started to use programming in several different projects that I'm working on with my students. Global water quality, I just got a very large data set and am setting it up in PostgreSQL, which I've found to be very challenging. And if any of you out there are experts in that, I could really use your help. A collaboration would be great. I'm learning how to use Python now, and I want to use that with geographic information systems, which I've used for a long time with commercial software. I have a PhD student working in Bangladesh who's collecting a lot of geochemical data and looking at how element concentrations change spatially and over time. I have another PhD student working on gas emissions. We collect a huge amount of data. Basically every 4 seconds we collect a bunch of measurements on gas compositions, and we do that for several weeks. So yeah, we have a lot of data to deal with. So we need to be developing automated, dashboards and so on for visualizing the data, doing statistical analysis, and so on. And so I'm hoping that the Data Science Institute will be a useful resource where we can learn and find new collaborations.
Hi, my name is Jesse Loker. I'm an assistant professor of finance at the Owen Graduate School of Management. What I'm presenting today is a project I've just started and how I think I have an inadequate approach, and I'm curious to talk with some of you later if there's some other smart people in the room that can help me solve this problem. So you're probably shocked to learn that as a finance professor, we care a great deal about where stock returns are going to go. And so we have lots of great methods, typically Bayesian methods, to try to predict through time. What I'm trying to do, however, though, is solve a problem where we're trying to look at the effect of short selling on asset prices, but really we only have very good data since about 2006 on this, okay? But most of our asset pricing tests that we want to run go back to 1965. So what I'm trying to do is I'm trying to impute data backwards in time, okay? So instead of going forwards, I'm trying to go backwards. And so one of the big problems we have in finance is that a lot of the typical methods, like k-fold validation, all these types of things don't really work because our data is clearly not IID. It's very heteroscedastic and also autocorrelated. So I'm borrowing some methods that are pretty typical in finance right up here, where we're using things like data embargoing, where we're removing entire slices of the data to try to break the autocorrelation, and using things called like a block bootstrap to try to deal with some of these features of the data. And I've got an initial result, which is up here, which looks pretty good, where I'm using, so the actual data in the first column is the most recent data in the last 10 years. And then I have done just a very basic, what I'm using now is actually a random forest model, which I'm not sure, I don't think is the best way to do this, but it's actually working okay right now. I just would like to make it a little bit better. So that's just a little bit about my research and what I'm working on, and I'm done.
Hi, my name is Alina Choi, Associate Professor of Biostatistics. My research interest is to find patient characteristics such as clinical factors or genotypes that can be utilized to reduce the variability in drug response so that we can find a better treatment. Pharmacokinetic studies or pharmacogenomic studies are very useful to identify this kind of patient characteristics, and we have been developing a system to perform this type of study using electric health record. However, this study requires very detailed, precise dosing information, and we found it's very challenging to extract this accurate dosing information from electric health record. Because oftentimes these information are embedded within the clinical notes as an unstructured form. So we have been developing the new natural language processing algorithm, and PhD student Hannah Wicks is presenting her new NLP system in her poster. So if you are interested in learning more about the NLP system we have been developing, please stop by her poster today. And so we have been successful to extract the accurate dosing information from EHR system. However, we found another challenging, that is the extracted dosing information are sometimes conflicting each other within even the same clinical notes. So now we have been developing a new statistical model that can be useful to identify which one is the correct medication dosing information. So thank you very much. Bye.
Hi, I will introduce you to FilterGraph. FilterGraph is a web-based data visualization service that allows anyone to go online, upload their data, and create visualization portals. Portals are interactive. Therefore, as you change the settings on the left of the screen, it affects the graph on the right side. And then you can filter the data as needed. You can use FilterGraphs to create scatter plots, histograms, and tables. A graduate student was using FilterGraph when she discovered the relationship between the flickering of a star and the amount of gravity on the surface of the star. This discovery was published in Nature. FilterGraph was used by NASA to develop the Transiting Exoplanet Survey satellite, which was launched into space last year. Finally, FilterGraph is now part of the Friest Center for Autism and Innovation, where we investigate how adults on the spectrum investigate the images it generates. Thank you.
Hi, everybody. My name is Will French, and I'm with the Advanced Computing Center for Researcher in Education, or ACRE. I'm going to attempt to give the slide without sounding like a car salesman, but if I do come off that way a little bit, I apologize. So ACRE exists to relieve researchers on campus of the burden of having to be hardware administrators or installing software and things of that nature. So we provide a lot of free training courses aimed at this mission, and in a nutshell, we provide resources that allow you to scale up your research beyond what's possible, say, on your laptop or on your, even a beefy server that you have within your own lab. So if you ever find yourself in a situation where you're running RStudio or a Jupyter Notebook on your machine, and suddenly, like, your laptop completely freezes up and it's out of RAM or something like that, that's a case where you're limited by your local resources. And so you might consider a resource like ACRE for overcoming that. We have a variety of different resources available. Some of our traditional high-performance computing tools include OpenMP and MPI, but we also have a number of tools that are geared towards data scientists. So R, Python. We recently stood up an instance of Jupyter Hub, which provides web access to an environment where you can launch and run Jupyter notebooks. And this is not traditionally our bread and butter. So traditionally, you can think of our environment as a cluster for batch processing. Is that 2 minutes? For batch processing, but we are moving more and more, as dictated by researcher demand, towards providing some of these interactive tools. Also GPUs. We have a lot of GPUs. If you're doing deep learning, machine learning, we have on the order of 200 NVIDIA high-end gamer cards within our environment that allow you to get machine learning done much, much faster than you could do without a GPU. Thanks.
Hi, so my name is Richard Galvez. I'm a Morse Known Data Science Fellow in NYU, actually, and before that I was a postdoc here, as some of you may know me. So I just wanted to take this 30 seconds, maybe less than a minute, to actually give you a kind of car salesman pitch on this particular data set that my group and I prepared. NASA has a spaceborne solar dynamics observatory, so 3 instruments that are monitoring the sun continuously. So it's been up since 2010, and so it provides basically, you could think of it as 15 channels of images and of the sun in various frequencies, and also it's 3 channels of magnetic information, magnetic field information. And my group and I, really what we were trying to envision was to create a data set that computer scientists and ML researchers could actually test some more complicated models on. Because at the end of the day, when you look at this, we have downsampled this to actually a reasonable resolution. It used to be each image was 4K by 4K. That's virtually, this is way too much for even ACRE's GPUs, maybe, I don't know. So we actually downsized to 512 by 512. But all in all, the data set is rough. It's more than 13 million images. So really, we wanted to kind of provide this data for the ML community to just go to town on it and tell us something new about the sun that we don't know already. And that was way more than 30 seconds, of course. And if you want more information, you could come find me and also check out the link on the top. Thanks.
Hi, I'm Rogers Hall, and with Dave Owens and Andy Hostetler, I direct the Space Learning and Mobility Lab in Peabody College. And I wanted to just share with you today an example of big data and what we call small activities. We're designing and studying things we call learning on the move. So you can see movement and interaction from 2 teams in this slide who are making and following a storyline about just how friendly downtown Nashville was to African American residents of the city in 1960. These are tour-like objects that they move through. Each member of the student team is wearing a camera on their chest, so we have audio and video. They're also carrying digital audio recorders. And each team has a GPS tracking device with them. So we can take the audio and video records and then map them in the city. To the left is a plan view of this time-space cube data structure, which is interactive and manipulable, and something we call the interaction geography slicer that was developed by Ben Shapiro in my lab, who's now at Georgia Institute of Technology. So on the left-hand side, you can see things like talk and media consumption pileup and heat maps. And on the right-hand side, we pull out one temporal dimension of that image, and we can see paths of movement for these teams going through the city, where they slow down and talk to each other, how they interact with the built environment, and things like that. I don't have time to share the results of this kind of analysis with you, but we think it's very powerful for studies of human interaction on the move and more generally learning on the move. Please contact us. Thank you.
Hey, I'm Jake Huey. I'm an assistant professor in biomedical informatics and biological sciences. I was only planning on a minute, so I can just stroll through this. So I really love learning about the world from data. And we study biological systems whose behavior changes over time. And a good example of that is the circadian system. So inside almost every cell in your body, you have a molecular clock that essentially tells the time, and you have a particular part of your body that receives input about the time of day it is. And these clocks synchronize your physiology and behavior to the external environment. And there's a lot we don't know about how the system works in humans, and we don't use our knowledge very well in medicine. So for example, maybe it makes sense to take particular medicines at particular times of day. So on the left here, this is a microscopy image of the circadian clock in a cancer cell that we took in collaboration. No, we didn't. This is just, this is one of my favorite paintings. But in any case, we are actively hiring here the couple of people in the lab right now, postdoc Darwin Fu and newly joined graduate student Dora Oboto. And so if any of this sounds interesting, then please come talk to me. Thanks.
Hi, everybody. I'm going to be reading as well. Once my slide is up. Oh. I expected too much automation. Apologize. I am Amish Makan, a computer scientist working at the health IT, working as a knowledge engineer at health IT at the hospital, as in Vanderbilt University Medical Center. And I've been integrating model-based, also known as domain-driven techniques, to clinical knowledge representation and analysis over a decade now. The result of some of these success stories were advanced clinical decision system implementations used across the hospital for patient management. And we have found that model-based techniques not only accelerate the information extraction or exchange with SMEs, but enable a tremendously rich set of analytical questions to be relatively easily answered. My examples on the screen show on the top an ontology of cancer management logic, or SMEs, built using our knowledge-driven domain-driven tools, from which, using certain domain assumptions that you see in the center, we create rich reports and visualizations on the health of the knowledge content. So this includes utilization, frequency, reuse of content, and so forth. This happens to be an n-partite graph where all the currently at the 90 or to 100 concepts are represented on the x-axis, and on the y-axis all the instances and their connectivity and relationship shown across as associations. And I also, just to finish off, I have a visualization of a report of a domain rule violations found in a pharmacogenomic knowledge base we currently utilize, and a small schematic of the architecture we typically utilize. If you have any questions or comments, please don't hesitate to reach out. Thank you.
Hi, everybody. I'm Hossein. I'm a postdoc in the NORAD lab. I'm a postdoc in the NORAD lab. So cells use signaling pathways, which is a network of the proteins regulating each other to make sense of the changes in their environment. Other than how much an environment changes, in our lab, we found that to my left in the top, how we are changing the environment on the cells, they are responding differently. Motivated from these results, I simulated the response of a signaling model from a well-characterized model under different perturbation that they are changing differently over time. And we asked the question, using this different input-output data, can we learn from the underlying regulatory networks? And what we find that when we are using all different input-output data to terrain shown in the red, we are able to get meaningful predictions as shown in the blue, yellow, and green colors compared to the data in the gray. And what we see is when we are using a specific type of inputs, the predictions are not getting better than 50–40%. And thank you.
Hi everyone. This is Johnny from Mechanical Engineering Department. I would like to talk about my group's recent progress in machine learning part. As we all know, many people may suffer about voice disorder needing surgery. At the meantime, the voice production is directly related with the vocal fold vibration. So therefore, our group's main research is to develop a computational modeling-based tool for vocal fold surgery. Right now, we have the capability to perform the patient-specific analysis on the 3D vocal fold vibration, as you can see from the figure. At the meantime, we still face the challenge about the unknown tissue property. Therefore, we develop a physics-based reduced order model to estimate the tissue property. This model is based on 1D momentum equation with entrance effect and loss effect to be decided. Right now, we are using high-fidelity 3D data to perform the machine learning to estimate the entrance effect and the loss effect. At the current stage, we are using 3 different conditions as shown here. So we are using case 1 and case 3 to train the model, and use the case 2 to verify our machine learning results. We can find from the very last figure, the machine learning model can give a very good prediction to case 2 results. So it motivates us to continue to doing this work. Thank you.
Hello, my name is Tim Warmentine. I'm an industry practitioner. I've been, led the analytics at Walmart, been various roles throughout my career. I started my own consulting company, and one of my first clients is a startup, and they don't have any data, right? So what we did is we created the data just using, random number generation. And it started getting really sophisticated, right? So we had to create all this data and then build models on it. But for the models to pick up this fake data, we had to create the correlations and all that kind of stuff. So this thing sort of evolved and had a life of its own. So I've come to realize that there's a lot of value and utility in being able to control the data that you model, right? So not all of it can be, and there's various ways you can do it. But I really think if you make data fun and you can create sort of different types of data structures, multivariate structures, hierarchical structures, that you can actually figure out what you're learning in a much more efficient way. So I think there's a lot of opportunity to do what you're doing, but do it in a little bit more of a controlled way. So, thank you.
Hello, everyone. I'm Amanda Moffett. I'm a postdoc in the Department of Physics and Astronomy, and I'm here to talk about one of my research projects, which involves measuring the metallicity distribution of galaxies. And by metallicity, what I mean is you can think of it chemical composition, or more specifically, the heavy element abundance in galaxies. And so we're doing this with a large data set, which involves 2 galaxy surveys, so the ECO survey and the RESOLVE survey, which are pictured up here on the left. ECO is the larger volume, and RESOLVE is the smaller volume that sits inside that. And on this plot, every single dot represents a galaxy. And for all those galaxies, we know lots of different measured properties, including their spectra. So galaxy spectrum looks like, on the upper right there, the squiggly line. And those sharp lines that you see are emission lines. And those lines tell us a lot about the chemical compositions of the galaxies. And in order to interpret those, you actually have to compare them to models of the physics in the regions where they're emitted. So these are emitted in emission line regions, like the H2 region that you see here in the middle. And we actually compare those observations with models using Bayesian inference to infer what the chemical compositions of those regions are. And you can see an example of that on the bottom left here. So each of these light gray lines is actually a metallicity PDF for an individual galaxy. And we're able to add those together and get a constraint on the metallicity distribution for a full volume of space, of all the galaxies that live in a volume of space. And so that's shown on the the sort of teal line here for the resolve survey. On the right, we have it for eco and resolve together. So now we essentially know what the metallicity distribution or chemical composition for a full volume of space looks like. Thanks.
Hello, I'm Gregor Neuert from the Neuert Lab. Yeah, I'm Gregor Neuert from the Neuert Lab, and we are interested in understanding cell-to-cell variability and how we can build predictive models. And what you see here on the left are individual cells in which we quantify RNA. These are molecules in these cells, and this variability is indicative of the underlying biology, and we think that if we can quantify this variability, here we can, so to say, ID the cells, and using this kind of ID, we can maybe in the future build better understanding of human diseases. And what we have done recently, we ask, what can we learn from this data and what can we not learn from this data if we use different type of modeling approaches? And here on the left, we compared the same data and with the same model, but we modeled it as either a mean and variance, or full distribution, and then made prediction for new data that we collected. And what we found is, if we compare the red data, which is our experimental data, to the predictions, we find that if we use a full distribution, we can actually make accurate predictions, whereas if we use just the moments or the higher moments, we are not able to make these predictions. And this is because our data is very asymmetric, like many data in biology, and because of that, standard modeling approaches fail because the underlying assumptions that are important for these modeling approaches are not fulfilled. And we believe that this kind of approach for modeling data to build predictive mechanistic models is not only important for biology, but for any type of data that is asymmetric. Thank you very much.
Hi everyone, I'm Ray Posek with Axial Healthcare, and we're very interested in identifying patients who are at high risk for adverse events related to opioid use. So in this mock-up, we have a machine learning model that's meant to predict opioid overdose. And this model uses a variety of features, some of which are modifiable, such as opioid dose and day supply and benzodiazepine use, and some of which are not modifiable, such as demographic information and medical history. And we can convey the overall importance of these different features using SHAP values, which we can then use to help educate healthcare providers on how to reduce risk of opioid overdose for their individual patients. But this is a lot of detail and data that someone not familiar with data science is not likely to grasp. So how do we summarize this information? Well, in this example, we can simply say that the patient faces a relatively high risk of having an opioid overdose, largely as a result of their opioid dose and benzodiazepine use, but a history of alcohol use disorder is also a contributing factor. So in conclusion for this talk, I want to say when you're doing data science in a business setting, know when to show the forest and know when to show the trees. Thank you so much.
Hi. Hello, I'm Regina Russell. I'm with the School of Medicine. I'm also a doctoral candidate at Tennessee State University. This is a piece of my dissertation that I'm talking about. So I am a social scientist, and I study knowledge practices, and particularly knowledge practice networks and organizations. And so my question is university research related to hospital outcomes at academic health centers like Vanderbilt, and there's about a little over 100 of those in the country. It's the little small box in the corner out of 6,000 hospitals, places that have universities connected to healthcare delivery. I used data from Web of Science to get what kind of research was coming out of institutions, and data from Medicare.gov, the hospital compare database, to see patient outcomes, and was able to show in a replication of some recent studies in Europe that the more cardiac-related research is happening at an institution, the better the heart outcomes, cardiac-related outcomes are at the hospital, lower 30-day mortality. I was also able to extend that to the social sciences and show that it is very similar for management research, and that more management research is related to lower incidence of hospital-acquired infections. Be happy to talk with you about it more if you're interested. Thanks.
Hello, I'm Su Quyên. I'm a research associate professor of biological science. So I hope everybody has a good sleep yesterday night, but I think that's not impossible because I'm going to tell you. So sleep problem is epidemic, a national epidemic, and it accounts for about $400 billion per year in the United States, and 1/3 of American population have the sleep problems. And we believe that sleep problems are caused by both environment changes and the genetics. And we know that genetics loads the gun and the environment pulls the trigger. So through the big data and the deep learning, and we will extract the associations and segregations among the particular sleep patterns and particular disease and the molecular defects. And then through the big data, and we also, big data does not stop here because we need to do we need to understand what does this mean, right? So together with Professor Carl Johnson, and we are interested in the monogenic disorder, which the disorder is majorly caused by one single gene's abnormality. So then we use a mouse model and to mimic what happens in mouse, and also use the human models. And then hopefully one day we can test the drugs and validate the drugs and repurpose the drugs. Thank you.
Good morning. My name is Lina, and I'm a postdoc at Biomedical Informatics, and I'm going to continue on the theme of deep learning in order to see what we can apply deep learning in NLP. Now, patients send a lot of messages to their healthcare provider to ask questions or express needs, such as, what are the side effects for these medications? Busy providers usually receive hundreds of messages per day, which can be overwhelming, especially if their message board looks like the first one. We trained a classifier, a machine learning classifier, that can identify what type of questions do the patients ask and assign labels for those messages. Do they ask logistic questions or medical questions? So the right healthcare provider from the first glance can identify what are the messages that I should actually respond to first. Nurses and clinicians will respond to the medical questions, while administrative staff will respond to the logistic ones. So we trained the classifiers on features that does not account for the semantics or the meaning of the words, such as bag of words. We also trained another set of classifiers that account for the semantics in the words, aka word-to-vec. Specifically, we trained convolutional neural network, a deep learning classifier, to assign labels for those messages. Our results showed that using CNN with semantics had the best performance compared to traditional classifier trained on bag of words such as random forest. Thank you.
Okay, I'm Christopher Thomas. I'm with Tila Wolmosdorf's lab out in psychology, and we are studying how people learn. We do this by setting up a puzzle game for them, nice structured environment, and measuring brain activity as they play the puzzle game and as they learn the rules of the puzzle game. The normal way that systems like this are built is to use a single workstation and to do the data analysis by hand. It's semi-automated, but you still have to make a human decision for every single data trace that you have. Both of these are bottlenecks. Typical systems top out at hundreds of channels. We're building a new system. It uses distributed acquisition hardware, so we're not limited by a single workstation, and it uses semi-automated and hopefully even fully automated processing to drastically reduce the workload for handling all of that data. Every time that channel counts have been increased in experiments like this, we've learned a lot of new and interesting things about how the brain works. So we are expecting really interesting things from this. If you would like more information about what we're doing, or if you're interested in collaborating with us, because the signal processing task is very open-ended, by all means, talk to us afterwards or visit our lab webpage.
My name is Kadir Choi. I work with Center for Asthma Research. So we do research to understand what and how asthma is caused. So to do that, we follow population from pregnancy or from birth to longitudinally. And we collect a lot of data, phenotypic data, molecular data, and also environmental data are related to those population. So the data accumulated over this long time is very large. We use those data to endotype the patients because asthma is very complex and heterogeneous disease. We need to divide them into different characteristics, also predicting what markers tell us somebody is going to develop asthma, and also illustrates a mechanism of asthma development using network analysis. But this data is large and complex and collected at different level. We need to use systems approach where we need collaboration with different disciplines, and we welcome if anybody interested in collaborating with us. Thank you.
Hi, I'm Darren Tyson. I'm a research assistant professor in the Department of Biochemistry, working with Vito Caranta on a National Cancer Institute supported Center for Systems Biology of Small Cell Lung Cancer. And the overall objective of the program is to understand how treatment response is controlled by tumor cell heterogeneity. We use and evolutionary dynamics, so we understand it as a dynamic system and trying to understand the tumor cell dynamics. We use a lot of data. We have data at many different scales. A lot of pre-existing data exists on human tumors, human cell lines, mouse models. Most of those data exist. So Ken Lau is part of our group as well. He mentioned earlier about the single cell data boom that is developing. Most of the current data is at the bulk level where tumor tissue is all ground up together. We are acquiring lots of data at the single cell level, both the molecular level in terms of nucleic acid sequencing, but also in terms of protein biomarkers as well. And a lot of these now are also being captured in temporal dynamics or with temporal dynamics. And we're trying to understand the relationship among these cellular states as they progress over time, especially in response to treatment. I'll leave it at that.
Hey folks, I'm Dan Work. I'm an associate professor here at Vanderbilt. I'm trying to make your commute just a little bit less painful. If you drive, I'm certain you have been caught in a phantom traffic jam. Okay? These phantom traffic jams are the jams that seem to have no obvious cause. There's no accidents on the roadway, there's no merge points, but in fact they're caused by the way that you collectively drive. Okay? These jams, they have a small variation in one driver's speed, get amplified by the cars behind, and all of a sudden you're stopped for no apparent reason. It turns out as vehicles become automated, we will take over some of the human driving tasks that lead to these jams, giving us the opportunity to either make these jams less prevalent if we design them well, or worse if we design them poorly. My team has shown in our prior work with a real autonomous car and up to 20 human drivers that carefully controlling these cars in the right way can kill these phantom jams from the roadway, benefiting all drivers by up to 40% in terms of their fuel savings when you compare the stop-and-go traffic to the smooth flow. So what are we working on right now? Well, we tested this in a very limited setting, closed course. We're trying to get to the next level on real freeways with real vehicles. Tennessee has a corridor that has 180,000 vehicles a day that are running through there. We're building the world's largest traffic sensor to cover this freeway so that as we put automated vehicle technologies on the roadway, we can understand how they interact with humans, how humans interact with them, and so we can hopefully get rid of these phantom jams once and for all. If you'd like to know more, please feel free to reach out to me. I think we're at the end of the session, but there may be a few more comments for our moderators. Thank you.
Hi, I'm Jesse Spencer-Smith, Chief Data Scientist for the Data Science Institute, and the unfortunate person who agreed to do a talk on live deep learning using data that we were collecting during the symposium. So I come up here with a plea. If you've not yet had your photograph taken, we need more data in order to have a successful presentation of the deep learning network. So over lunchtime, if you want to step right outside, it'll only take less than 10 seconds if you're willing to do that. But at the same time, we don't want you to miss the presentation of the student awards. So grab your lunch and then have your picture taken, but do come back in here. But wait for instructions from Lindsay.
Okay, thank you to all of our lightning speakers. We really appreciate your work. So we're about to break for lunch.